Hi friends, today I am going to discuss a very important topic related with chemical bonding, that is MO theory. All of us know that molecular orbital theory is the most updated theory and it explains various aspects of chemical bonding of various molecules. Now, in your class 12 classes you have learned in MO theory about the homonuclear diatomic molecules. Today I have taken up a different example, heteronuclear diatomic molecule, say for example carbon monoxide. Why I have chosen this topic? It has a background history, because while you are learning coordination compounds, people used to talk about synergism or synergic bonding. Now if I talk about synergism, now carbon monoxide, this molecule is a very unique molecule. Now when we are talking about metal carbonyls, okay, it is seen that the linkage of carbon is with the metal. But if you think out of the box, I am saying, if you think about carbon and oxygen, which one is more electronegative? Obviously the answer comes to be oxygen. Then why not the bonding is through oxygen? Why it is through carbon? And that is why we call carbonyls, and carbonyls are very stable compounds, and you know they have huge application, and there are separate branch of chemistry called organometallics where it has extensively studied, also in metallurgy. So today I will be discussing the MO diagram of carbon monoxide and you see how I explain its reactivity. Thank you. You just come to the diagram. Now I have to explain the diagram a little bit. As you know that a concept of MO is based upon LCAO, linear combination of atomic orbitals. The same is applicable over here, but the picture is a little bit different from that of what you have done in homonuclear in nitrogen, obviously, because the two atoms are not having the same electronegativity. You can see this is carbon and oxygen. This is 1s2, 2s2, 2p2. And this is for oxygen. You can see that the 1s orbital of oxygen is a little bit lower than the 1s orbital of carbon. The same is applicable for the 2s, for the 2p. Why? Because oxygen is more electronegative than carbon. So that atom which is having a higher electronegativity, its atomic orbital will be lower in energy. So this is actually an energy profile diagram. So we are actually doing an energy profile plot. So you can see that the atomic orbitals, they intermix to form some hybrid orbital or mixed orbital, which then react to form the MO. So this is the MO of carbon monoxide. Now just see 1s2 and this 1s2, so they combine to form two MOs, one bonding, one anti-bonding, one sigma and one sigma star. Now this is 2s orbital and this is 2p orbital. Now if I think in this way, that this 2s and 2p, and here also 2s and 2p, they intermix among themselves. So this is not that hybrid orbital that we learnt in hybridization, sp. It is sp. It's not like this. It's not sp. No, it is sp. Means its s character is more and p character is suppressed because it has mixed with the p orbital. Here also it is ps. See, it is close to p. So p character is more and s character is less. Here also the same thing we have drawn, that s and p, they intermix between themselves and they have formed sp and ps hybrid. Now this sp hybrid now comes and forms a non-bonding orbital which is localized on oxygen, that is 1 sigma non-bonding. And you can see that this ps and this sp, they are now same in energy. So when two orbitals are same in energy, they will form an MO, and that forms 2 sigma and 2 sigma star. So how many electrons? 1, 1, so 2 electron. Okay, then so one orbital has come here, so how many orbitals remain? 2 orbitals remain. Okay, so these 2 orbitals, they, and here also you can find that these 2 orbitals are also in a they are also the pi type of orbitals. So this 2 and this 2, so 4 orbitals, so they form 1 pi and 1 pi star. 1 pi, so how many electrons are there? 3 electrons are here and here 1. So how many? 4. So 4 electrons have formed the 1 pi orbital. So they have gone to the bonding situation. And this ps, so what is this this electron coming from? So this ps is actually forming a non-bonding orbital which is localized on carbon. Okay, so this is called the HOMO, highest occupied molecular orbital. So in the formal charge calculation also you can see the carbon has a negative charge. This is the formal charge, that is number of valence electrons of carbon, that is 4, minus number of electrons on the lone pair of carbon, that is 2, minus half into 6, that is minus 1. So actually the HOMO is localized on carbon. So when we are talking about carbonyls, it is the carbon which is donating its negative charge to the metal, and we get like NiCO whole 4, FeCO whole 5, and we get a lot of carbonyls, mononuclear and binuclear or trinuclear carbonyls. So that means, and this is called the LUMO, that is lowest unoccupied molecular orbital. So you know that this type of ligands, it can act as a good ligand, can undergo the phenomenon of synergism, that is they are sigma donor come pi acceptor. So they accept electrons from the d orbitals of the metal, so they accept in this pi star orbital. Now if I go to the, so the reactivity is in this way we can explain, and also here you can see that the dipole moment of carbon monoxide is very low, it's 0.2 dBi. Why it is 0.2 dBi? You can find in the structure that oxygen bears a positive charge. If you go for the formal charge calculation, you can get it. So obviously oxygen being an electronegative atom will not try to be positive. So it is attracting the electron cloud from carbon. So since it is attracting the electron cloud, obviously its dipole moment is decreased, because you know dipole moment acts in the negative direction. But since here oxygen has a positive, so some of the negative from carbon is snatched from oxygen and we get a very low value. Now if we go for the bond order, then half into 8, how this 8 comes? This is the 2 electrons from the 1 sigma, the MO configuration is written 1 sigma, then 2 sigma, this don't include the non-bonding electrons, 2 sigma, then 2, then 2, 4, then 2, this you should also consider this pi because it is in the bonding situation. So here 4, so 4, 4, 8, minus 2, which 2? This 2 electrons. So the bond order comes to be 3, so you can see it's triply bonded. So I think you have understood that what happens, why my question was that what was the important query is that why the bonding is through carbon. It is because you can see this 2 sigma non-bonding is an orbital which is localized, which is formed from this ps hybrid orbital which is localized on carbon. And what about the sp hybrid? Why not from oxygen? You can see its energy, this sp hybrid gives rise to this 1 sigma non-bonding. So this 1 sigma non-bonding is having much lower in energy. So can it donate to the metal ion? Obviously not. So this is a very important thing, and also you can try these molecules also. You can compare the MO of carbon monoxide with nitrogen because both are 14 electron system. You can understand the difference. Also you can think about cyanide and NO plus. So carbon monoxide, cyanide and nitrosyl all are isoelectronic species. So their MOs will be identical, but if you find the reactivity with metal ions, their reactivity will obviously vary. So this is we will be discussing in our next class, in our next video about the the stability. We will compare the stability of the complexes. Hope you have understood the video. If you have any queries, then please write in the comment section. I am ready to answer. If you have liked the video, please like and share this video and subscribe to my channel. Thank you.